Hi, I'm Adrian, and today I'm going to talk about our work on few shot detection without retraining, titled FS-DETR, few shot detection transformers without prompting and without retraining. Broadly speaking, current few shot object detection methods can be categorized into two broad categories, retraining based and without retraining. The former assume that at test time and prior to deployment, the provided samples of the novel categories can be used to fine-tune the model. The latter can be deployed as is and can detect new classes on the fly. Our work is focused on improving the latter as it's more practical for deployment thanks to its sans training nature. More precisely, our main contributions are a fine-tuning few shot detection prompting method capable of detecting multiple objects at once with support for an arbitrary number of samples per class and classes. This feature can and are enabled by extending DETR on two key ideas. Firstly, feed the provided visual templates as visual prompts, and secondly, stamp these prompts with class-agnostic pseudo-class embeddings predicted at the output of a decoder alongside the bounding boxes. We note that most of the prior work focused on adjusting the features of a faster RCNN after ROI pooling using cross-attention or by modeling the classes using a relationship graph. Finally, the remaining ingredient is in the form of a simple and efficient yet powerful pipeline consisting of unsupervised pre-training followed by prompt-like based class training. Starting from a DETR-based architecture consisting of a CNN feature extractor and encoder and a decoder, we adapted to accommodate OpenSet FS-D by proposing to provide novel classes templates as additional visual prompts in order to condition and control the detector's output. These prompts are added in addition to the object queries normally processed by the decoder. To train the system, we also propose to stamp these prompts with pseudo-class embeddings akin to soft prompting, which are then predicted by the decoder along with the bounding boxes. We note that these pseudo-class embeddings are class-agnostic and are associated randomly to a given template at every training step. This can be viewed as an analogous component to the traditional positional embeddings. Prior to this, the visual prompts themselves are obtained by passing the template through the same CNN encoder used by DETR, with the special features being aggregated via global overage pooling. Note in the figure that the visual prompts go on to interact via cross-attention with the encoder, which has the effect of preserving the most closely relevant features, and in the decoder, where they are processed as the rest of the normal object queries, with the notable difference that the loss continues to be applied only at the end of the object queries. The proposed changes allow us to preserve the main characteristics of the DETR architecture. Hence, the loss itself remains unchanged conceptually, with the objective now being to predict the bounding box locations and the pseudo-class added, with the matching performed using the Hungarian matching algorithm. Now, while the training procedure described previously works, it's somewhat restrictive, especially given that DETR-based frameworks tend to be more data-hungry than their faster RCNN-based counterparts. Hence, to this end, we propose to introduce a pre-training stage in the few shot detection process. The framework itself remains largely unchanged, except that because we don't have any ground truth data, we use selective search to identify a set of object proposals based on which we define the templates. Upon augmenting them, the system has to then learn to localize them and distinguish from the rest of the patches. As the table on the right shows, this step is crucial for training a high-performant FS-D system. Here are some visual examples showing the output produced by our approach. The input template is shown on the left of the pair, while the output on the right. Red boxes are known classes, while the green the new one. Notice that the prediction is stable with respect to the input examples. When comparing our approach with other methods that don't require pre-training, we can observe that our approach outperforms them across different regimes. Similar conclusions can be drawn on Microsoft Cocoa too. Thank you for listening, and I hope to see you by our poster. Feel free to drop an email otherwise.